Welcome back. In this video, I will be talking about the SN1 reaction. So if you want to know more about this reaction, see examples, and learn more about its properties, this video is for you. What does SN1 tell us? The S stands for substitution, the N stands for nucleophilic, and the 1 means unimolecular, meaning that there is one thing that determines the rate of this reaction. So the SN1 reaction is a nucleophilic substitution reaction, which just means that we are going to replace the leaving group with the nucleophile. The mechanism for the SN1 reaction is as follows. You're going to start with the nucleophile, the solvent, and your reactant, also called your substrate, the thing attached to the leaving group. In step 1, the leaving group will leave. This creates the carbocation intermediate, which is the molecule with a positively charged carbon atom. At this stage, if it's possible to make a more stable carbocation, rearrangements will occur. These may include hydrogen shifts, methyl shifts, or ring expansions. In step 2, the nucleophile will attack the carbocation, binding itself to the molecule. In step 3, if necessary, deprotonation will occur to remove the positive charge from the nucleophilic atom. Deprotonation is simply the removal of a positively charged atom. Usually it's a hydrogen removed from the nucleophilic atom, i.e. the atom that attacked the carbocation. In summary, in the SN1 reaction, the leaving group is going to be replaced by the nucleophile. You should also be aware that sometimes the solvent also acts as the nucleophile, and in these cases, the reaction is called a Savalas' reaction. Now let's talk about the energy diagram for the SN1 reaction, in which energy is a function of time, meaning that energy changes as time goes on. Notice here that the tips, or the highest points in energy, are going to indicate transition states. The trough in between the transition states is going to be the intermediate. Specifically, in this case, it's going to be the carbocation intermediate. The number of transition states is going to correspond with the number of steps in the reaction. Now, this is a diagram indicating that there are 3 steps in the SN1 reaction, the third step being the deprotonation step we just talked about. Looking at this diagram, try and figure out what the molecule looks like at each step. At the very beginning, it all starts with the reactant, aka the substrate. Then we have transition state 1, in which the leaving group is beginning the process of leaving. So at this point, the leaving group is partially bonded to the substrate as it's leaving. In transition state number 2, the nucleophile is partially bonded to the carbocation. Finally, we have the third transition state, and this is the deprotonation process, in which that proton is partially bonded to the nucleophilic atom as it's being removed. Now let's take a look at the intermediates. Intermediate number 1 is going to be the carbocation intermediate. It's going to be the molecule with a positively charged carbon atom. Next we have intermediate number 2, and this is going to be when the nucleophilic atom has a positive charge on it, right before it's deprotonated. And finally, to the very right, we're going to end with the product. And so that's how you read these diagrams to figure out what the molecule should look like at each point in time. Now what about the rate of the SN1 reaction? The rate law says that we're going to multiply the rate constant K by the concentration of the substrate. This means that the rate of the SN1 reaction depends on one thing only. It depends on the concentration of the substrate, aka the molecule with the leaving group. Therefore, if you double the concentration of the substrate, you're going to double the rate of the reaction. If you triple the concentration of the substrate, you're going to triple the rate of the reaction, and so on. Now it turns out that the 1 in SN1 tells us quite a bit about the rate. For example, it tells us that the SN1 reaction is a first-order reaction and is a unimolecular reaction. These things basically say the same thing, that there is one thing that affects the rate of this reaction. If the carbon you're reacting at for this SN1 reaction is a chiral center once the nucleophile is attached, it turns out that more of the inversion product than the retention product is going to be made. The inverted or inversion product is the product with an opposite RNS configuration from the reactant, and the retention product is the product that retains or keeps the same RNS configuration as the reactant. Now here's a question for you. Why do you think more inversion product will be made than retention product? We can figure this out by thinking about how the nucleophile attacks. To make the inversion product, the nucleophile will attack from the opposite side as the leaving group is leaving. To make the retention product, the nucleophile is going to attack from the same side as the leaving group, which means there are 2 things that have a negative charge, which we know same charges repel each other, and so you have these 2 things repel each other, which means the retention product is going to be slower to make. In contrast, the inversion product is faster and easier to make, and therefore more inversion product will be made. Now what about the reactivity of the SN1 reaction? Regarding the nucleophile, SN1 reactions prefer weak nucleophiles that usually have a neutral charge. Regarding the solvent, SN1 reactions prefer polar protic solvents, which help stabilize the carbocation and thus make it easier for the leaving group to leave. In polar protic solvents, the order of reactivity for halogens is as follows, from best to worst: iodine, bromine, chlorine, and fluorine. And this is when we are talking about halogens as a nucleophile in a polar protic solvent. Now what about carbocation stability? Well, it turns out that the more stable a carbocation is, the faster the reaction proceeds, the faster the leaving group can leave. From most stable to least stable, we have tertiary, secondary, and primary carbocations, and finally, as the worst, we have a methyl carbocation. Now what about the leaving group? Well, for SN1 reactions, the better the leaving group, the faster the reaction. And the worse of a leaving group you have, the slower the reaction will go. Good leaving groups should be weakly basic by themselves once they've detached from the molecule. Now that we've covered some major points of the SN1 reactions, we're going to do some practice problems. So if you're looking for a challenge, definitely stick around because we're going to go through some interesting examples that progressively get more difficult. First up here, we have a Savolysis reaction in which we're going to react this molecule with this solvent, which is also going to act as the nucleophile. Now remembering what we said about SN1 reactions, we're going to be replacing the leaving group, which in this case is going to be chlorine, with the nucleophile. Okay, so first step is going to be that the leaving group leaves, which is going to give us this carbocation. So we're going to have that positive charge right here. The next step of this reaction is going to be the nucleophilic attack. So the nucleophilic atom specifically will be oxygen. It's going to bind to the carbon here, and we will get this result because oxygen itself is bonded to the ethyl group here and the hydrogen. Now, those two lone pairs are left over, and so oxygen has a positive 1 charge here. Now, because we'd like the oxygen to have a 0 charge, we're going to deprotonate, meaning we're going to remove this hydrogen atom. So we're going to use more of the solvent. The electrons from this oxygen are going to go attack and take off this hydrogen. These electrons here are going to go back to the oxygen on the molecule. Okay, and so now this oxygen has a 0 formal charge. So this is going to be our product. Now notice that this carbon is actually a chiral center, which means we should have the retention and the inversion products. So in one of these, we're going to have wedged oxygen, and in the other, we should have the dashed oxygen. Now, as we said before, more of the inversion product will be made, and so we'll expect this product to be in majority. Now take a moment and try this example on your own. Draw up the mechanism for extra practice. So we're doing an SN1 reaction, which means the first step is that the leaving group leaves. The leaving group will be bromine, and that's going to give us the carbocation intermediate, which looks like this. Next, we're going to have the nucleophile attack. As a small note, Me stands for methyl and is just a CH3, and then we have the OH, like this. So these two are the same thing. The nucleophilic atom will be oxygen. It's going to go ahead and attack the carbocation, and we're going to get this product. Notice that we need to deprotonate now because oxygen has this positive 1 charge. So we're going to take more of the solvent, which is going to attack here, taking this hydrogen off. These electrons from this bond between hydrogen and oxygen will go back to oxygen here, and we're going to get this product. All right, so what about inversion and retention products? Well, it turns out that even though there are no chiral centers in this molecule, we do have isomers. We have trans and cis isomers. Because if you draw it like this, so I'll draw this one wedged, this molecule is going to be different from if the oxygen is dashed. These two are going to be stereoisomers. Okay, they're going to be cis and trans isomers. Now, this one over here in white is going to be cis, and this one over here is going to be trans because the groups are on the opposite sides. All right, so you should expect both of these products to be made. And here, as we just saw, no rearrangements were necessary because when we had this secondary carbocation, there was no way to make it a better carbocation as these carbons here did not offer any opportunity for rearrangements. Remember, methyl and hydride shifts only happen when you have something possible at these adjacent carbons, and ring expansions only happen if you have a ring smaller than a 6-membered ring. So if we have a 6-membered ring already, there's no ring expansion. Now try this example on your own and see what you get. This is a relatively friendly example. We're doing SN1, so the leaving group should leave. After chlorine leaves, we're left with the carbocation here, and then we have water. Water will be our nucleophile and our solvent, so again we have another Zeinalov reaction. We're going to attack the carbocation, and we're going to produce this product. Now, oxygen here has a positive 1 charge, so again we're going to deprotonate. We're going to take off one of those hydrogen atoms. Okay, so we'll take this one off, give these electrons back, and we're going to make an alcohol. Now there are no chiral centers and there are no isomers of this molecule, so this is the product that you will expect. Whether you draw the OH group wedged or dashed, you have the same molecule. Now what will be the products of this reaction? The leaving group is going to be iodine. Now how do I know that? Well, I know that OH- is a very strong base, and therefore it makes a very bad leaving group. And so iodine will be my leaving group. Once iodine leaves, we are left with this carbocation. Okay, now we need to check for rearrangements. This is going to be a tertiary carbon, which if we were to move a positive charge to it would be a tertiary carbocation, which is more stable than a secondary carbocation, which we have here. So we need to shift something. Now the question is, should we move the methyl or should we move the hydrogen? Well, it turns out that you're going to end up moving the hydrogen, and you're going to have a hydride shift. So in a hydride shift, the hydrogen and the positive charge are going to switch places. So what we should have is this molecule over here. We'll put the hydrogen here, and we'll put the positive charge here. Now that we have the most stable carbocation that we can have in this molecule, the nucleophile will go ahead and attack. The nucleophilic atom is going to be the oxygen, and we are going to produce this molecule. Okay, and oxygen here has a positive 1 charge. So we need to deprotonate. Oxygen will take away this hydrogen, these electrons will go back to this oxygen, and we will be left with this product. Now the question is, will you have 2 different products? So let's look at this carbon. Is this carbon a chiral center? Well, it turns out it is, because it has 4 different groups around it. And so we would expect 2 types of products. In one case, we would expect the methyl to be wedged and the oxygen to be dashed. In the other product, we would have the opposite case. Alright, and so these are going to be your 2 products for this reaction. Now so far, we have seen cyclohexanes, but they haven't been in the chair conformation. So let's try this out. So still, we're doing an SN1 reaction, which means the leaving group should leave in the first step. That should give you this molecule over here. We'll make the carbocation like this. Right, then the nucleophile is going to attack, after we have checked that no rearrangements are going to happen in this example. Alright, so nucleophile attacks, and we're going to get this product. Now we need to deprotonate, which will give us an alcohol. So this is going to be one of our products in which the OH group is equatorial down. Now remember, because this is an sp2 carbon, which means it's flat, the oxygen could have attacked from above. And so if it attacked from above, then another product we could have gotten is this one over here. And then we'll point the methyl group down. Now between these 2 products, which one do you think is more stable? Should we prefer the methyl group pointing up in the axial position, or should that place be taken by the OH group? Now if you think about it, methyls have 3 hydrogens attached to them. Okay, so you have this kind of very bulky group here, and so you would prefer that the methyl is pointing downwards, all right, and the oxygen to point upwards. Okay, and so you would expect the blue product here to be the more stable one. In the end, you'll have a mixture of these two products. Now, what would you draw if I asked you to draw the products of this reaction? We are talking about an SN1 reaction, so the first step should be that the leaving group leaves. After this leaving group has left, we are going to be left with a carbocation. Now, remember, in SN1 reactions, rearrangements are possible. That includes hydrogen shifts, methyl shifts, and ring expansions. We have a 4-carbon ring here, and 4 carbon rings will expand to go to 5 carbon rings. And so we're going to have a ring expansion here. We're going to draw a 5-carbon ring. The question is, where should the positive charge go, and where should this methyl group go? Well, taking into account that this right here is the bond that broke, and I have simply put these electrons from this bond over here, so that in the end we have a shape that's somewhat like this. And I number this, so I'll say 1, 2, 3, 4, and 5. I can also number my new ring. So at carbon number 1, I should have the methyl group. Now, carbon number 1 now has 4 bonds, because it has this implied hydrogen. This carbon here lost a bond from this bond breaking. So we would expect carbon number 2 to carry the positive charge. So after this, you're going to take a look at this molecule and ask yourself whether this carbocation can be even more stable. So right now it's secondary, but we have a tertiary location possible. So what we're going to do is a hydride shift. Again, the hydrogen and the positive charge are going to switch places. Therefore, we have a positive charge here now, and a hydrogen here. That's implied. Now that we have our tertiary carbocation, the nucleophile will attack. Then we need to deprotonate, okay? And essentially what you're doing there is just removing an H, and so this will be your product. That's the end of this video. I really hope you enjoyed it. There's a link below if you're interested in my publications, science and math tutoring, or my website and more free content. Thanks so much for watching, and I will see you next time.